Morning. Let's get started. So the next homework is out. I think I put it to release at 8 a.m. this morning. It's on communication primitives, which we did a couple times ago, and about Bitonic sorting, which we will do today. Everybody okay? Is everybody able to see the programming assignment? The next one? People looked at it? Any questions? Okay. I'm sure there will be questions. But yeah, please look at it earlier rather than later because it's more complicated than the previous one. So just to get a sense of what is going to be involved. It's about implementing some of the communication primitives that we talked about in class. Cool. Yeah, so like I said, today we are talking about Bitonic sorting, which is a classic parallel sorting algorithm invented in like the 50s. Yeah. So we talked a little bit about sorting earlier when we were talking about multi-threading. Like, do people remember like when we talked about merge sort and how to do merge sort in parallel? Okay, cool. Yeah. So that was mostly for shared memory when we were talking about like work span analysis, and today we're going to do it for distributed memory. Though you can implement Bitonic sort on a shared memory machine, of course. Anything you can implement for distributed memory, you can implement like a shared memory version. But the algorithm design is going to look a little bit different, and I'll talk about like why we can't just why is it not so easy to use the merge sort that we had? So which algorithm can serve as a good starting point for parallel distributed memory sorting? We have O of n squared algorithms, we have bubble sort, insertion sort. And we have algorithms that reach the lower bound, which is n log n in the comparison model. So we have heap sort, we have merge sort. For randomized algorithms, we have quick sort, and so on. So we have a lot of potential options. And as we have seen, like divide and conquer is usually a pretty good idea for parallel programming because it divides the subproblems. It divides the problem into separate subproblems, which is nice when you want to work on them separately. So if we think about merge sort to begin with, we divide the list into two equal size lists, and then we merge them back together. This is the occurrence for the work. So T of n, you have two subproblems of size n over 2. You sort them, you have to merge them in time O of n, and that's n log n. Okay. So if we were to implement this in distributed memory, first we have assume that we have n items and p processors, and we just divide the problem in half, and both of those halves can happen in parallel. So that's n over 2, p over 2. And then for now, this O of n is the merge. So we do know an algorithm for doing parallel merge, but for now we're gonna just look at what happens if you don't parallelize the merge. Similar like we did last time. Well, if you unwind this recursion, you get this n over 2, p over 2 becomes n over 4, p over 4 plus n over 2, and all the way down. So you unwind, and you get n over p. You unwind this p times. This becomes 1, and this is a summation n plus n over 2 all the way up to n p over 2. And then if you solve this, that comes out to n over p log n over p plus n. Yeah, so this is good in some ways, in the sense that there's a p outside over here. So that's kind of indicating that we are getting p-ish speed up, but we can't use more than log n processors. And that's kind of what we saw similarly when we did the work span analysis, like the same idea. We had log n parallelism, which is also not good because we want to use much more than log n processors. So we need to parallelize the merge, and we have the algorithm, this algorithm that we had last time to parallelize the merge, which is like you have your two things that you want to merge, and you choose the midpoint in the bigger one, and then you do a binary search into the smaller one, and you divide in half. And the argument hinges on, it's not an even split every time, but it is reducing by a constant, it reduces the problem by a constant factor size every time. However, the issue with this in distributed memory is the subproblems are uneven. So it's harder because one, there's load balancing issues. Like if you imagine this on different processors, you might have to shuffle more of the data around because now your subproblems are unevenly split. And also ideally, all your problems are of the same size, which is not true here. Like they are similar sizes, but maybe they're like a factor of 2 off of each other. So this is not ideal for what we want to do. Yeah, so any questions so far? People remember this? Okay. All right, So Bitonic sort is a sorting network-based algorithm, and sorting networks are, you can think of them as like a set of wires, and each input is on one input wire, and the wires are connected through these. So the input wires are horizontal, like this, like X and Y here are inputs, and the the way it works is that you have these vertical lines, and these are comparators. So if you have a plus here, like this is a circle, this is a plus, and this puts, if it's a plus, it puts the min on top and the max on the bottom. So this comparator is just taking the min and the max of the two elements that it connects and swapping them if they're out of order. So like if X is already smaller than Y, this is not going to change the ordering of them. But if X is greater than Y, then it will swap the ordering of them on the wires. So like after this point, if X was bigger, then this would become like YX. And on the other side, we have like the inverse, which is the decreasing one. And it's just the same, except then the max would be on top. So this is like minus, this is plus. And yeah, so if X was less than Y, then X would show up on this wire, moving on, and Y would be swapped over there. And you build sorting algorithms with the set of wires, like vertical and horizontal. And basically, if you have a bunch of wires that are like, they can be in parallel with each other. So if you imagine many horizontal wires, we'll see pictures later, but you can imagine many of them, and disjoint sets of them are connected by wires or by these comparators. And so all the swaps can happen in parallel. And one really nice thing about that is that the swaps happen in a predetermined setting, in the sense that like no matter what your input is, as long as it's the same size, it uses the same sorting network, which is not really the same for merge sort, because like depending on your input, the merge may look different, like the split looks different. So this is nice to think about for parallel computing, because the algorithm is always fixed up front, and it's just the actual items that are swapped, they're different, but all the comparisons are fixed up front. Yeah. And the speed of a sorting network is proportional to its depth, which means like the depth of the circuit, similar to what we were talking about. If you imagine this like the depth being how many, kind of like how many layers of these comparisons do you need to do. So if you can do them all in parallel, that's like adding one like phase of them in some sense is adding depth one to them. So that is sorting networks. And like I said, you build an algorithm based on these comparators. So the network structure is like this. You have these inputs, and then these boxes are the comparators, and they may swap along the wires. And then you may have to do some synchronization, which means that like you do all these comparisons, and maybe you need to make sure that the comparisons have finished before you move on to the next set of comparisons. And yeah, so each one of these columns is one vector of comparisons, and then you can build an algorithm based on these phases of comparisons. And the comparisons happen in parallel. And one reason that people are interested in this is that is well suited. So you can do these comparisons in like, if you imagine like writing your code just regularly on your CPU, you can of course do these comparisons. These kinds of things are especially well suited to other kinds of simpler architectures. Like there are architectures just based on networks, or there are architectures like that are less expressive or less general. Like for example, GPU architectures. We won't really talk about GPUs that much in this class, but basically the idea is that they have many tiny threads, and the threads don't like it if you do different things on them. So that is why they're well suited to sorting networks, because for sorting networks, you can imagine like each tiny thread gets one of these wires, and then you do these comparisons. A Bitonic sorting network is one example of a sorting network. And first, to understand it, we have to learn what a Bitonic sequence is. So a Bitonic sequence, it's just a sequence of numbers, but rather like a monotonic sequence is either monotonically increasing or monotonically decreasing. And a Bitonic sequence is just two monotonic sequences. So there's two parts. The Bitonic sequence, it's either first increasing and then it's decreasing, or it could be the other way around. It's first decreasing and then it's increasing. So like this example, this increasing part is 1, 2, 4, 7, and then the decreasing part is 6, 0. Yeah, and like I said, if it was decreasing and then increasing as well, that would also be Bitonic. And we'll see later that you can also consider cyclic shifts of Bitonic sequences as Bitonic sequences. So this is this one is not Bitonic, 892104, like 892104. But if you rotate it, you get 048921, which is Bitonic, because this part is going up and this part is going down. And you can notice that if it is a cyclic rotation of a Bitonic sequence, this part is going to be higher than this part if you're going to do the rotation, because it has to be, like if you imagine a picture, like the left part is going to have to be moved. The right part is going to have to be moved onto the left part in the rotation. So at a high level, this Bitonic sorting network, it sorts n elements in log squared n time, and it rearranges. So basically, the way it works is that you're going to get an unsorted sequence, and we're going to arrange it into a Bitonic sequence. And using the properties of the Bitonic sequence, we are going to arrange that Bitonic sequence into a sorted one. We're going to see how that works. But you can see that this is not work efficient. Like it takes log squared parallel time to sort n elements, and serially, we know that not even serially. Anyway, we know that the lower bound is n log n, which is log n time per element. But we will see that it is still worth studying because it's like a classic algorithm, and also sometimes you can pay a little bit in the work to get more parallelism. Questions? Okay. So the first core subroutine in Bitonic split, or in Bitonic sorting, is called Bitonic split. And like I said, this algorithm, this algorithm is from Batcher in 68. And this Bitonic sequence, like I said, it has two parts. It has an up part and a down part, or reverse, a down part and an up part. And suppose that we have a Bitonic sequence, A0, A1, up to AN minus 1. And this is saying that suppose that it was perfectly split in half. The up part is the first n over 2 elements, and the down part is the last n over 2 elements. So you go up, and then you start coming down halfway through. And suppose that we partition this Bitonic sequence into two subsequences, where you start comparing, like you can kind of think of it as like a two-finger stepping. So you put one finger in the beginning and one finger at the halfway point, and then you go forward from there. So you're going to do n over 2 comparisons, and you compare them each, and you put the smaller one into S1, and you put the bigger one into S2. And then you're going to get something that looks like this. S1 is going to go up and then down, and then S2 is going to go down and then up. Is it obvious that they will look like that? I'm going to claim that they will look like that because, so for example, if you keep your fingers, like one finger starts here and one finger starts here, and you're going to walk this way and this way. And so at some point, you're going to reach some inflection point where this thing becomes smaller. Wait, sorry, this thing becomes bigger than this thing. And then so that's like this picture. These are all the things that are bigger, or these are all the things that are smaller than like this upper part of this triangle. And these things are smaller than like this part. And then vice versa, the other way. So this is kind of, this is some, and one nice thing about this is that all these comparisons were happening in parallel. Like there's no dependence on them, and the size of these two subsequences is always fixed. It's always n over 2 for both of them, which is also nice because you don't need to think about splitting, or you don't need to think about like what size you're going to partition them into. And it is nice that using this Bitonic split, so this is called Bitonic split, where you do this like two-finger walking and min-max comparison. And it is interesting that if you had a Bitonic sequence of this form, you would get out two Bitonic sequences as well. They might not be equally split. Like this one was perfectly split in the middle with n over 2. These two might not be perfectly split. Like the inflection point might happen anywhere, but they will be Bitonic, just with some arbitrary inflection point. And they also have this property that for all x in S1, which is the min, and for all y in S2, which is the max, x is less than y. So all the elements in S1 are smaller than all the elements in S2. And you can just see that kind of by construction. And one cool thing that Batcher noticed is that if you recursively apply this function, given this Bitonic sequence of this form, if you recursively apply the split function, you will eventually get a sorted sequence. Well, split and then merge, which we will talk about. And it works for any Bitonic sequence, even if they're not equal sized. Yeah. And this is just a concrete example. So L1 and L2, these are the input. Yeah, these are the inputs actually. So L1 is an increasing Bitonic sequence. L2 is also an increasing Bitonic sequence. And to get like the structure that I talked about, where you go up halfway and then down halfway, you can reverse L2, and then you just kind of like you don't necessarily even have to concatenate them. You just start this comparison here, this way. L1 is just laid out in order as it was. L2 is laid out in reverse order, and then you just do these pairwise comparisons. And so L1 here, 2 is less than 23, so you put it into L min, which is the smaller one. 6 is less than 16, you put it into the smaller one. And then on the other side, the max gets put into L max. And then, like I said, at some point, there's this crossover. This is increasing, and this is decreasing. So at some point, everything after here is going to be bigger than everything after this point. So like here, there's a crossover. 8 is smaller than 10, but 11 is bigger than 9. So 8 goes into here, and then 11 goes into... So 8, which was on the left side, goes here, and 11, which was on the left side, goes there. Like I said, all the elements in L min are smaller than all the elements in L max. Oh, yeah, and I guess any monotonic sequence is also technically like a bitonic sequence. It could also be considered bitonic even if it's just monotonic, because the other part is just empty. Like theoretically, it could be the case that like if all elements in L2 were bigger than all elements in L1, then they would just be partitioned in this way, like L min and L max. So the other part would be empty, but that would still be fine. Yeah, and we can make some argument. This is just making the argument about why, like I said earlier, that all the elements in L max would be greater than all the elements in L min. And you can make it concretely with some algebraic statements like this one is bigger than this one is bigger than this one, and then the crossover point means that they will be partitioned in the right way. Okay. Yeah, so this is the algebraic part of how you prove this. Prove that you can do it like prove that the max of L min is at most the min of L max. So the biggest element in here, biggest element in here is smaller than, or is at most the smallest element in here, which means that all the rest of them are going to be at most whatever's in here. And yeah, you just prove that with the indexes, and then there's several case analysis. Yeah, xk is this thing, xk plus 1 is this thing, and then xk is at most this thing, because otherwise it wouldn't have been put into L min. And then this thing, the transition point is at most the point at which you start putting stuff into max, and then you just use transitivity. Questions? Okay. Yeah, so this is Bitonic split, which is like you partition this Bitonic sequence into these even parts, or not necessarily even, but evenly sized, but the inflection point is not necessarily even. And this is like the core part. One of the core parts of how you do the Bitonic sorting is you take a Bitonic sequence and then you split it into a new Bitonic sequence. Yes.
So are you just going to prove in general? You're trying to use xk for the element, but xk plus 1 for L max. Why can't we use the same thing?
What do you mean the same things to compare them?
Like same indices, because you're using a different k for calculating the min and for the max.
You're using a different k. Oh, you're saying like why is this k and why is this n minus k?
Well, no, not that. Why are we using k for max and why are we using k plus 1 for min? Like if you want to
K
compare
for
L min
max.
and L max.
K is in x sub k is in min and L sub, or sorry, yeah, xk is in min and xk plus 1 is in max.
Yeah, the other way.
Yeah. Wait, no, it is this way, right? Because max of L min is max of xk and n minus k minus 2. Y sub n minus k minus 2. Like the stuff in red is in min and the stuff in blue is in max.
Oh, that max.
It's a good. I guess one question is like, why do we have to reverse this? Like, why is this not just k? I think it's because like they reverse the list, so like they want to keep the actual. If you want to keep the actual list, you don't actually do the reversal. You just do it in the indexing. So I think that's why it's like n minus k and k. Can I answer your question? Thank you. Okay. Okay. So using this thing, we're gonna analyze this. T and P is the time. There's three components so far in this algorithm. There's three parts. The first one is both halves were sorted. If you remember, we had two halves. We reversed the second half, and then we did this Bitonic splitting. So the first step is to recursively sort. So that's just this recursive thing, n over 2p over 2. To do the pairwise comparisons, you can do them all in parallel. So that's n over p. You can do them perfectly in parallel. And then afterwards, you get L min and L max. Everything in L min is smaller than everything in L max. So if you resorted L min and L max, you could just concatenate them, and the whole thing would be sorted. And that again is T n over P, P over 2. So you get this recursion, T n over 2, P over 2 plus n over P. And if you unwind this recursion all the way down, this 2 part is exponentially increasing on the way down, and this n over P part is decreasing. No, it's n over 2p over 2. So this part is like fixed. You do the same number of comparisons at each level of the recursion, but you're just doing it on the sublists. So if you keep unwinding, this 2 is increasing in powers of 2, and by the end, this 2, they're log n levels of recursion, and p 2 to the log p is p. And then this thing is n over p times log. Okay. So this is not ideal because these p's cancel out, and you get p times n over p log n over p plus n. Or sorry, this red box is p. Sum of powers of 2 up to p is p, or sum of powers up to 2 of p up to p over 2, but it's a constant vector off, and times n over p. So n over p times p is n. So that's where this n in the end is coming from. And this thing here is p times this thing, n over p log n over p. So yeah, that is the analysis of this initial thing. And this is not ideal because this is even worse than the merge sort that we had initially, even when we were doing serial merge. So if you remember, merge sort was n over p times log n over p. But this is n times log n over p, which is a p factor off. So that is not ideal. And so the issue came from this recursive formulation, which is t times n over 2 p over 2, or sorry, 2 times this thing. And where did this come from? Well, there were 4 sorts. The first half, we had 2 sorts, 2 recursive sorts to sort the first 2 halves, and then we had to sort L min and L max again. So there are 4 sorts, and each of them could happen 2 at a time. So that's why you get this 2 over here. And yeah, so that is not ideal, and we're going to have to cut this down. And the main observation in Bitonic sorting is that L min and L max are also not arbitrary sequences. So like when we did this thing, this would work no matter what structure L min and L max have, because you could just, as long as they have this property that like everything in L min is smaller than everything in L max, you could just sort them and you would be done. They would just be in order. However, we're going to try to leverage some property of L min and L max to make this part smaller, because as you can see, this is not working out. And one thing that you can notice is like in the in the initial splitting that we had, which is like they were perfectly up and down, or perfectly halfway is the inflection point, and then you do this Bitonic split. The two output sequences were Bitonic. And one question that we can ask is like, is this true in general? Like if you keep going down the levels of recursion, is it still true? And we are going to show that it is actually still true. Does that make sense? Okay. So like I said, in Bitonic splitting, you do this, you initially have this, something that looks like this, which is like, goes up for n over 2, and then it goes down for n over 2. And then you do this walking. So one finger is on the halfway point, one finger is on the start. So you compare square with square, circle with circle, triangle with triangle, all the way down. And you get one Bitonic sequence, and you're going to split it into two child Bitonic sequences, Lmin and Lmax. And it was in this case, but maybe we may be concerned that it's not true in general cases because it may not look as nice as this, exactly where you started halfway. And our goal is to avoid the second part of splitting, or to avoid the second part of sorting, because we saw that we'll screw up the recursion. We want to apply repeated Bitonic splitting, and we don't want to do additional work. We don't want to keep sorting the second half. We wonder if you just keep applying these splits, no matter what you got on this second half here, are you going to keep getting Bitonic sequences? And you don't want to do any additional work. Like we don't. If you remember initially in the sorting networks, you swap the elements, but we're not actually doing any other additional work besides swapping. We are not actually reversing the sequences. We are not doing additional sorting. We're not ever figuring out where the inflection points are because that is too much work. And I think that's kind of cool actually, because it seems like you would have to do additional work. Okay, so here's some visualization, and we're going to prove it algebraically in a little bit, but this is visualization to see how the proof is going to go. So you have two sequences, S1 and S2, they're both Bitonic, and we did this Bitonic split. So you put all the smaller ones in S1, you put all the bigger ones in S2. And this is what the initial one looks like, up and then down, and then, so like the halfway point is here. So this is just showing like where the first one is walking and where the second one is walking. Okay, so this is how so first we're going to construct Lmin, or S1, they called it here. So we start here, and then we start walking this way. Okay, and this is cool because this one is increasing, and then this one is decreasing, and we know by the way that this was constructed that eventually once we get here, we're going to have to switch over to here because there is some point at which these match. And so you would just move over at the point at which like this one swaps over, and then you would get something that looks like this, which is up and then down. So that is good. It's promising. And notice that this inflection point was not halfway through. Okay, the second one. So this is Lmin, and then we're going to do Lmax. So you start from the left side, and then you go right. And like it's kind of the reverse of this one. So we first start taking elements from this thing, and then at some point, we first start taking elements from here, because the way that this was constructed, it starts bigger than the red part, because the beginning of the red part was put in min, and at some point when min starts, or at some point when the red part starts being larger, then you start taking elements into this, and then you start taking elements after that. There's another swap over point. You take elements from this part, just going down. So it has this look that's like down, up, and then down again, which looks potentially problematic because we want something that goes up and down or then down and up. But if you remember from what I said from the beginning, we also consider Bitonic sequences that can be cyclic shifts of something that is just up and down or down and up. And the high level proof is going to be like, this is not necessarily initially looking Bitonic, but if you rotate it in some, there's a rotation under which it will be Bitonic. And how you're going to prove that is basically about the endpoints. So, does that make sense so far? So we're going to make an observation about the properties of this Lmax. And we can notice that by construction, we're just going to call these endpoints, the starting point is A and the ending point is B. And by the way we constructed it, A is at most B because we got them from the blue part, and the blue part is monotonically decreasing. So, like in the ordering of B, in the ordering of the blue part, A must have come after B. So A must be at most B because it was monotonically decreasing, and so from that you can see that Lmax is a cyclic shift of Bitonic sequence because this part is decreasing, and then this part is decreasing, and this is bigger than that. And yeah, and also to be clear, like I said, we're not actually ever doing these rotations because if you did want to rotate this into what was looking better, like up and then down, you'd have to find the inflection point, which is going to take you at least log n, which is additional work that you don't want to do, and then you're going to have to do the rotation, which is going to take you some time, which you also don't want to do. So to be clear, like in the actual, when you do the, so this splitting is recursive. Like we had, in the beginning, you start with something halfway up and then halfway down. You do this Bitonic splitting, and then you just keep splitting down on the children. It's like a recursion. And you don't ever have to make it into a nice form where you do the rotation. This is just for analysis. Okay. So if we go one further level of recursion, we had something that looks like this. This is the second half, and we're not actually, like I said, we're not actually doing further rotation. So we have something that looks like down, up, and then down again. This is like Lmax. And Lmin has no problem. Like we just showed that it's going to be up and then down. And we had showed in the beginning, it just falls into the first case again, that the splitting is going to give you these two cases. And the only sort of unfriendly cases like this, where it's like down, up, and then down again. And so we make a similar argument like we did before. The first half is going to start here, the second half is going to start here, and then you're going to do the walking left to right. So these are the two halves. And we're going to start here. Yes, we're going to start here, and then we're going to walk this way until we get to something bigger here. And then this part is going to decrease. And then on the right side, so this is Lmin, and then Lmax. The bigger stuff starts here. You walk down until you get some inflection point in red, and then you get the remainder in blue. And it's going to follow the same property that A and B, like A is the start point on the left side, and B is the start point on the right side. A is going to be at most B because of the way that the sequences were decreasing. Does that make sense? Yes.
We proved that if you perform Bitonic split on a Bitonic sequence, it will get like Bitonic sequence or something that can be shifted. But we didn't prove that something that can be cyclically shifted into Bitonic sequence when you do a split on that you still get to Bitonic.
I see. Yes, this is what this is trying to prove. Yeah. So maybe let's, yeah, so this part is actually harder than the first part. So let's do it again. So this thing can be cyclically shifted into, this thing can be cyclically shifted into a Bitonic sequence. And this, we know from the initial argument that this endpoint is bigger than this start point because like this is decreasing and then this is still decreasing and then this is like the actual min. And then you just rotate it to get a Bitonic sequence. And so by the same argument, this thing in here, anything in here, must be bigger than the starting point in here. Because this endpoint is bigger than this, and this endpoint is the smallest element in the second blue part. So let's say this is just the halfway point. This thing is going to for sure be bigger than this thing. And so when you're taking L min, we're going to start taking from here because this is smaller. And so you take all of them from here because all of these in here are smaller than all of them in there. So you take all of them from here, and then you take some of them from red until you see something bigger than what's in here. And then at that point, you switch from red to blue. So you switch from in here to something in here. And that's this picture, which is you took all of them from this part, and you take some of them from this part, and then you take some of them from this part. So that is min. And then for max, we have the reverse argument. So we're still walking like the same way, but with the reverse argument. And the important part, again, is that this right blue part is bigger than that left blue part. So we start taking from this right blue part first. And actually, we take all of them, or all of them that weren't consumed here. We take, like, from the starting point in this second blue part, you keep walking, and you take them all until you reach the inflection point with A, or with red. And then from there, you take the remaining red things, and then, like, then maybe there's this little part, which are going to go into max because this part was smaller. So this was a cyclic shift of a Bitonic sequence, and these have similar structure, which again are cyclic shifts of Bitonic sequences. And we have this property, A is at most B, because like it comes from the property from the first part, all the things in the left blue part are smaller than all the things in the right blue part. And these come from the left blue part, and these come from the right blue part. And same for the other side. And so, again, because this was a cyclic shift of a Bitonic sequence, these are again cyclic shifts of Bitonic sequences. Did I answer the question? Thank you. Yeah, that's not obvious at all, I guess. So, yeah, and the most important part of that was that we had to use that this everything in here is bigger than everything in here, which we got because this is a shift of Bitonic sequence. Okay. So we can prove that algebraically. Like that was just pictures, but you can actually prove it using indices, and we can use it. So we're gonna have to start. So the way that this proof is gonna start is you have to use the definition of Bitonic sequence, which, like I said, there's three cases. One is that the first part is increasing or non-decreasing, I guess, and the second part is non-increasing. So that's kind of like up and down. They could all be flat technically, but it just needs to be monotonically increasing then monotonically decreasing. And then the second case is the first part is down and the second part is up. And I use down and up. They're kind of like visualizers. They don't have to be actually numbers down and up, but it's easier to think of it that way. And so that's case 1 and 2. And the third case is that there's a shift that you can get into case 1 or 2. And these are some examples. So this one, 3, 5, 10, 15, 3, 4, 7, 10, 15. This is the turn, and then 14 down up to 1. So this is up and then down. Then the case 2 is down and then up. So this is 14 down to 1, and then going back up to 15. So then that's down and up. And then the last one is a shift. So down, up, down. And so if you think of like what we were saying, A and B, here A is less than B because, so this part is going up starting from 1 and then going down starting from 14 and then going down again, 8, 4 here. So if you put 8, 4 at the end here, then that would be up and then down. And this is smaller than that. 8 is smaller than 9. Okay. So that is the formalism. And then we can also formalize this Bitonic split just using these indices. So Bitonic split is you have the sequence L0 up to, or sorry, X0 up to X minus 1. And then L min is you just take the min of X0, Xn over 2, X1, X over n over 2 plus 1. And then L max is doing the same comparisons, but just max rather than min. So it is clear that there are n over 2 of these comparisons. And like the things that you're comparing are n over 2 off of each other. Okay. Yeah. So the first lemma that we want to prove is given a Bitonic sequence, and you have this thing, L min and L max, that you got from the Bitonic split. We want to prove two things about what we got. First, L max and L min and L max are Bitonic, which we were showing with the pictures. And the reason that we want to prove that is so that we can just recurse on the two halves without additional work. And we want to show that the max of L min is at most the min of L max, and this allows us to avoid sorting in the subproblem or in the recursive levels. You can just keep going down. The high-level algorithm is that we're going to have the two halves that are sorted. Like if you remember, we had the two halves, and then we rotated one, or we reversed one to get like one single Bitonic sequence. So we get the two sorted lists, and then we avoid sorting. We reverse the second one, and then we keep applying this split. Okay. So the proof is actually not that hard, but it's just like mechanical. You just have to go through the cases. So, like we can use the cases for Bitonic sequence that we had, T1, like type T1, and so on. And this is so type T1 is like up and then down, and we can show that here there's just this case if x0, which is this one, is greater than xn over 2, which is like the halfway point, then that means the inflection point x0 is, yes. So that means the inflection point had to be between x0 and x minus xn over 2, because like it's going up and then going down. So that means xn over 2 is like after the inflection point and is lower than x0, like this picture. And so L min would just be, in this case, all of this, the second half, and L max would just be all of the first half. And then you can do like the other side, which is x0 is less than xn over 2, which is then you have this kind of case. The inflection point came after xn over 2. And then you do a similar type of argument. There has to be some crossover point here. L min is Bitonic. L max is like this, but it has the property of that you can shift it. So that is two subcases of first one. And then, yeah. So case 2 is T2? Oh, yes. Okay. There's two cases under x0 is at most. X0 is less than xn over 2. The first case is that, so it's always, oh, okay, I see. The second one, the first one is at the inflection point is after. The second one is at the inflection point is before. And then you make like a similar argument like this. You will not have to prove this on your homework. It's just for illustration. Okay. And yeah, this sublemma is, it's very similar to what we have been saying. It's that if you have a Bitonic sequence and then you have a cyclic shift, if you, yeah, a cyclic shift of the Bitonic sequence, if you split your sequence into L min and L max, and you split the shifted thing into L prime min and L prime max, then L prime min is a shift of L min, and L prime max is a shift of L max. And that just comes from how we constructed it. Yeah. And you can prove that just like with how we constructed the Bitonic split, which is that you compare x0, xn over 2, so on. So L min would be like if the inflection point is k, or if the rotation point is k, then you're comparing xk with xk plus n over 2 mod. So like the same comparisons are being done when you do the rotation. It's just that they may not happen exactly in the same order that they happened in the initial Bitonic sequence. Yeah. So if you have this rotation, you're not changing the fact that the resulting sequences will be Bitonic. nor are you changing the actual elements in the resulting Lmin and Lmax. You're just changing the order of them. So after we do all the Bitonic splits down to the bottom, we have to do something called Bitonic merge, which is you do all these Bitonic splits, and then you have to put them back together into a sorted sequence. And this is a picture of how you do that. So this is the original sequence, which is what we got by doing the, like you sorted both halves, and then you reverse the second half. So this part is going up 3, 5, 8, 9, 10, 12, 14, 20. The second half is going down 95, 90, 60, all the way down to 0. So that is the input into what we're going to do for the Bitonic splitting. And basically the way it works is that it's like recursion. So you first split it into two halves. And you do the split like you do the walking. So the first pointer is here, the second pointer is here, and you just walk them along. And these are all going into Lmin. Red is Lmin. So these are all going into min. And then at some point they flip over. And then 20, yes, 20 is bigger. So it is going to Lmax. So 20 and 0 were swapped. But that is the only thing that did not respect the Lmin and Lmax partitioning. And you can see that this one is Bitonic. It's going up because you just took everything from red into the last one, which is going down. And then this one is just the reverse. This is going down up until 18, and then it goes back up into red. So that is the first split. And then the second split, you do 4 and 4. You do this two subproblems, half and half. So first is 8 and 8. Now it's like 4, 4, 4, 4. And so the 2 pointers are now here, 3 and 10. And then you walk this way. And so this is going up. 9 gets swapped with 0. These are the comparisons. And otherwise, yeah. So this is Lmax, and this is Lmin in the subproblem. And then same on this side. You take, this is Lmin, this is Lmax. And so you notice like we swapped 35 and 95. We swapped 23 and 90. We swapped 18 and 60. And then we swapped 20 and 40. And this is now down and then up. And this is also just down. Yeah, and you keep doing that. So like that was size of 4, and now you do size of 2. And one nice thing is that actually any sequence of size 2 is a Bitonic sequence because it's either up and down or down and up. But you need them to, we still need to do some swapping perhaps because they need to respect like Lmin and Lmax. So even though they are Bitonic sequences, they may not follow the, like it needs to be less than and greater than. And here, so for example, like 60 and 40 get swapped into Lmin, 95 and 90 get swapped into Lmax. And then the base case is you do it in case 1 in size 1, and then you just, the one on the left is smaller than the one on the right. Yeah, and notice that at the end they're all sorted. 0 up to 95. Yeah. So if you have a Bitonic sequence of this form, like half up and then half down, and you apply log n Bitonic splits, then at the end you will get something that is fully sorted. And the complexity for this Bitonic merge, if you have one element per processor, is log p, because it's log n levels, and all of the comparisons can happen in parallel. And if you notice, it happens to respect hypercubic permutation, like with the comparisons. They're all, like here, they're all distance 8 from each other. Here, they're all distance 4 from each other, distance 2, distance 1. So they're off by 1, like you just flipped a bit. Yes.
There's no particular like word sequence for it besides working with the elements because through the splitting itself.
Yeah. It's called, I guess it's called Bitonic merge, but it's just a sequence of splits. Thank you. Yeah, good question. So I glossed over like so if you got an original sequence, if you got a Bitonic sequence in this form, you could just do this. I glossed over how you would get here. Basically, you can apply the same algorithm just to the two halves. You would do like yeah. If you get two sorted halves, you just reverse the other one. Yeah, so like I said in the beginning, you can implement this with a sorting network. So you do this sequence, your inputs on wires, and you do the comparisons. There are log n columns. Each column has n over 2 comparisons, where you just do like the Bitonic split. And if you have, there's two forms of this Bitonic merging network. One is, like I said in the beginning, there's two directions, like plus and minus, and that's just like which direction min and max are in. If it has plus, you make an increasing sequence. If you have minus, you do a decreasing sequence. And so this is how you get the two halves, where you don't actually have to do any. If you have the sorting network, you don't actually have to do any reversing. Like we just think of it like that because it's easier to think about. But you could put the sorting network, but you put minuses rather than plus, and then in the end you would get a decreasing sequence. Like if you had a network to do sorting, increasing, and you replace them, you replace some of them. Yeah, I think you replace some of the comparators. Then in the end, you can also get something that does decreasing, and so you don't ever have to do reversal. Yeah, and this is a picture of the Bitonic merge that we just did, which is just the comparison. So here, like the source is smaller, and the dest is bigger. Yes, the source is bigger and the dest is smaller. So you're putting all the small stuff on the left half, top half here. You're putting all the bigger stuff on the bottom half, and then you recursively do that. And this is just a similar example, but now 16 rather than 8. Yeah. So this is just the same numbers that we had in the beginning, like 3, 5, 8, up to 95. And the second half is starting here and decreasing. And so these are all distance 8 from each other, and they're connected. This is one column in the sorting network. Like the stuff that's in boxes, that's one column of the network. But you need to, all these comparisons need to happen before you move on to the next column. And the depth is log n. There's log n columns. Yeah, and all of these proceed in parallel, which is cool. And like I was saying, this layout, it doesn't matter what the input numbers were. Like we just happen to put input numbers on them for concreteness, but it could be any input and you would still use the same columns, which is nice because you don't need to do anything dynamically. Like in merging, you need to dynamically partition to do the parallel merge, or you have to serialize the merge, which is also not good. Okay. So in Bitonic sort, so that is the core part of the Bitonic sort. And we did like the second half, which was if you have a sequence which is like up and then down halfway, how do you sort that using the Bitonic splits? You need to get there somehow. And we're going to get there. First step is to build the Bitonic sequence, and then second one is to use this merging network that we just showed to sort that using Bitonic split. Yeah, and how are you going to build that? Well, you can do the same thing that we have been doing pretty much with Bitonic merge, but you just use that to build the two halves. And this is your connection, this is your sorting network. And one thing to notice is that they're not all plus like they were in the previous thing, like plus being the one direction of the sorting. Here is like plus minus, plus minus, plus minus, plus minus, plus minus. And the reasoning for that is because you want, like I said, minus gives you decreasing. And so you want decreasing on the second half. And to get that, we put bigger ones here, smaller ones here. Sorry. Yes. And then those are going to feed in to the next. Yeah, those are going to feed into the next, like the way that the wires are connected next. Like, go back. Like the inputs or the outputs for here are the inputs for the next column. And similarly for here, the outputs for here are the inputs into this one. And doing this swapping allows you to put the decreasing order on the second half without ever having to do the reversal. You just point the arrows in a different way. Yeah. So this is an example. So this initial sequence is unsorted. 10, 25, 9, 3, 8, 12, 14, 90. This is the same numbers, but they're just completely randomly ordered. And we're trying to put them into this thing that we had initially, which is like up and then down. So 10 and 20 are swapped, or 10 and 20 are fixed because we're going, max is going on the bottom part and min is going on the top part. 5 and 9 are swapped because this is minus. So 9, max is on top and min is on bottom. And same here. Now this is plus again. So 3, 8, min is here, max is here. 12, 14, min goes here, max goes here. Or sorry, max goes here, min goes here, and so on. So they're flipped. And then the reasoning for that is, so here we had min, and here we had max. Wait, hold on. Oh yeah, because you have to do this comparison later. Yes, because this Bitonic merge gets you two Bitonic, like this is recursive as well. So yeah, so this is like 2, which is the base case, and this is distance 1, which is the base case. This is distance 2, the recursive call is distance 1. This is distance 4, the recursive call is distance 2, then distance 1. Yeah, and so that is why, like, so here in this initial step, this is plus, so 9 is going to go up there. 9 would be up here, like min and then max. But then in the next step, these two get swapped. So min and then max. So, and then 5, so this would be like 9 would go up here, 10 would go down there. And then in parallel, this is happening. 5 would go up there, 20 would go down there. So that's why you're comparing 5 and 9 in the second step of the recursion, in the recursion. Yeah. And then similarly for the next one, you do the recursive calls 8, 4, 2, 1. That makes sense? So these are all like Bitonic. This is, I guess, another level of Bitonic merge. The settled part, hard part, is that each of these is recursive as well. Yeah. So, like I said, each of those are recursive, and this is 2. This also becomes 4 and 2. This also becomes 8, 4, 2. Yeah. And this is just an example, a similar example. Yeah, where you do the final output, which is sorted. Okay. So the depth of the total network is log squared. So that if you remember, the depth of the merge at the end was log, because there are log n levels. And the depth of the first path is log squared because you have log n levels, but each of those has log n under log of, sorry, you have like k up to log n levels of this initial thing, but each of those has log underneath it. So it's like 1 plus 2 plus 3 up to log, which is log squared. And that comes from this summation. Each stage of this network has n over 2 comparisons. And if you were to implement this serially, that would be n log squared n, which is not reaching the lower bound. But we still may prefer this in some cases because how nicely it fits the sorting network. Yeah. And this is the pseudocode. And you can see it's very simple. There's two loops for I up to log p minus 1, for j down to 0. And then this is just compare exchange is like what is on the wire. So this is compare exchange. Pointing this way, so max min goes on top, and then this is min goes on bottom. And and you figure that out with the parity of the ith bit, which is what is on the outer loop. So the outer loop is like how it's like the different levels of the Bitonic merge that we just saw, like 2, 4, 8, and so on. And then for each of those, you have to go down to 0. And the way, yeah, so you determine which direction you're going through the parity of I plus 1, and then you figure out who your partner is through flipping the jth bit, which is the distance. Yeah, so you start from higher distance and then you go to lower distance. Yeah. So this is the last slide, I think. Just to finish up. So we said that the parallel time is log squared p, or log squared n, I guess. But if p is equal to n, then you have log squared p. The computation time is log squared, and the communication time is tau times log squared p plus mu times log squared p. So it's like you have log squared p levels, or order log squared p levels, and then each of those has tau, which is one level of latency, plus mu, because you're just exchanging, everybody is exchanging one number. But there are n over 2 numbers exchanged, but they all happen in parallel, and none of them conflict with each other. So that's why it's just mu, because there's no serialization. And if n is greater than p, we can see this pattern all the time, which is if you have like n over p numbers on each processor, you just do the local problem first, and then you somehow do some exchanging. So step 1 would just be everybody has n over p elements. You sort them locally using whatever sorting algorithm you want, like merge sort or anything. You could use Bitonic sort also. Then you run Bitonic sort at the higher level, but now so now you have you still have the wires, but rather than each one having one element, each one now has n over p elements. So you cannot just do the regular compare exchange that we had before, because that was just defined for one element. And you're not just going to swap the entire list with each other as well, because that also wouldn't work. So merge split here means you have 2 sorted lists. Like we sorted the local elements, so now every processor has a sorted list. Merge split means that you have 2 sorted lists, you merge them together, and you just split them in half, lower and bigger. So you get like the bottom half is on one, the top half is on another. So that's kind of like an analog for min and max, but when you have multiple elements. The computation time is this thing, n over p overall, log n over p times plus log squared. They're log squared levels. Yeah, notice that this log squared is only in p. It's not in n, because the Bitonic part is only on the processors. But this part, this is the local sorting part. You have takes n over p times log n over p to sort n over p elements. And then this is the Bitonic part, and this n over p is now in front. This used to be like 1, but now it's n over p because you have to, when you do the merge split, there's n over p elements in them. Communication time is, notice it's also in p. It's tau log squared, they're log squared level of synchronization, so that's tau. And then you have to communicate n over p in each round rather than 1. So that's mu times n over p, and you have log squared p rounds. And I think that's it. Yes. Questions? Yes.
How does the sorting network calculate the specific bits of Bitonic?
How does the sorting network? It does not need to. So notice, like the sorting network, the sorting network does not actually ever do any rotation. The sorting network is just doing comparison. And the rotation was it's for analysis purposes. It's just to show that if you have a Bitonic sequence that you can get to one that looks nicer under rotation, then if you do a split, you would also get to new Bitonic sequences under rotation.
So how is that property maintained if we do any sort of rotation?
Because like if you remember these kinds of pictures, this top one is a Bitonic sequence under rotation. or like how do you, or the question is like how do you know that they're still Bitonic sequences? Because you have to leverage the property of Bitonic sequences that this right part is bigger. Sorry, the smallest element on the right half is bigger than this biggest element on the left half. So yeah, that is like really subtle. So to be clear, you don't ever actually have to rotate them into something that looks nicer. It's just for analysis purposes, and we showed like in the sublemma later that if something is a Bitonic sequence under rotation, if you do the Bitonic split, the if you had it in the nicer form, you would get the same element in Lmax. You would just get them in a rotated order. So you're not, you don't violate the Bitonic property that way because you're doing the exact same comparisons of elements. Like normally, if it was in a nice form, it'd be like 0 and n over 2. If k is the inflection point, then you're still doing like k and k plus n over 2, which would be in the nice form like 0 and n over 2. So you're still doing the exact same comparisons of the elements, you're just doing them in a different it's not even really a different order because they're all in parallel, but they're just going to show up in a different order in the output. But it's still going to be a Bitonic sequence under rotation. Good question. Well, it's nicer for load balancing for one, because with merge sort, like if you parallelize, so if you serialize the merge, then we have that would be fine for distributed memory, but it would be not very parallel. And if you want to do the parallel merge that we discussed earlier, that causes an issue for distributed memory because uh, load balancing is an important issue for distributed memory. Like you want the processors to have approximately even amounts of work because then one processor might finish much faster than another one, so everybody would have to wait for the longest running one. And that is not an issue that's not like a theoretical issue necessarily, but it's a practical issue. You can prove similar bounds for the parallel merge for this one that would be like good asymptotically, but um, you would be bounded by like the max and both in terms of computation and communication. So that is so Bitonic split is preferred, or it's there's also well later on we'll do like an algorithm called simple sort that uses Bitonic sort as a subroutine. So that is actually maybe more preferred practically, but this is like an important theoretical concept to understand like how you so this you can evenly partition the work perfectly because you just do n over 2 comparisons and they're all nicely paired according to like the bit representation. So, yeah. Other questions? Then that's it for today. Thank you.